All right, more sample problems for Chem 111. So today we're talking about empirical formulas and solving for empirical formulas. So first, let's look at the hydroxylamine hydrochloride is a powerful reducing agent which is used as a polymerization catalyst. It contains 0.5 or 5.80 mass percent of hydrogen, 20.16 mass percent nitrogen, 23.0 mass percent oxygen, and 51.02 mass percent chlorine. What is the empirical formula? So we know that the empirical formula is the smallest whole number ratio of atoms or moles in the compound. So which means that if we look at this, we're solving for, there's going to be Y number of H's, X number of nitrogens, Z number of oxygens, and some number, which I'm going to call A, because we ran out of X, Y, Z, number of chlorines. And what we're looking to solve for is these smallest whole number ratios, but we want it in moles. So we're going to find a way to convert from this mass percent into moles and then divide by the smallest. So the first thing, this is all a percent. Right? So we can assume 100 grams total. Right? Which means if we have 100 grams, mass percent is the mass of that ion or atom over the total mass. If we have 100 grams, this percentage then becomes grams of that atom. Right? So we're going to say that that becomes 5.80 grams of hydrogen, 20.16 grams of nitrogen, 23.02 grams of oxygen, and 51.02 grams of chlorine. Right? But we need to convert this again to a moles, so we're going to have to go through the molar mass for each one of these. Right? So we want to convert from mass to moles, so we have to use the atomic mass for each one of these. And we see that from the periodic table, 1 mole of hydrogen has a mass of 1.008 grams. 1 mole of nitrogen has a mass of 14.01 grams. 1 mole of oxygen has 16.00 grams. And 1 mole of chlorine has 35.45 grams of mass. So if we do this calculation for each one, we say that in this 100 grams, that is going to represent about 5.75 moles of hydrogen. 1.439 moles of nitrogen, 1.439 moles of oxygen, and 1.439 moles of chlorine. So since we want the smallest whole number ratio, we're going to divide each one of these by the smallest value present, in this case, is any one of these. So we're going to divide all of these by 1.439. So when we do this, we're going to end up with, for hydrogen, it's the only one that's not, we can have approximately 4, and each one of these is going to be 1. Which means our empirical formula, these values go into this equation here. So we're going to have H4N1O1 Cl1, or H4NOCl. This is going to be our empirical formula for this hydroxylamine hydrochloride. Let's look at another example where we're taking a compound containing chromium and silicon, contains a mass percent of 73.52 mass percent chromium. Determine the empirical formula. Again, we want an empirical formula for chromium that has some amount and silicon, which has some amount, which is Si. Right. But since there's only these two things, then the mass percent of the chromium plus the mass percent of silicon has to equal 100%. Right? So since we're given the mass percent for the chromium, the mass percent of the silicon has to equal this 100% minus the mass percent of chromium, which is 73.52%, which gives us a mass percent for silicon of 26.48%. Right? But we don't want mass percent, we want an actual mass. So again, we can assume 100 grams total, which is going to change these 2% into a mass. Right? Because we want the smallest whole number ratio. So now we have, then this compound contains 73.52 grams per 100 gram of chromium and 26.48 grams of silicon for this 100 gram total. Right? Again, we're going to convert to moles. So 1 mole of chromium from the periodic table is 52.00 grams, and 1 mole of silicon from the periodic table is 28.09 grams. Again, do this math, 73.52 divided by 52, we're going to get 1.414 moles. If we do this other one, 26.48 divided by 28, we're going to end up with 0.9427 moles. Again, because we want the smallest whole number ratio, we're going to divide by the smallest number, which in this case is this bottom one, 0.9427 moles. If we do this bottom one, we're going to end up with 1. And the top, this ends up being about 1.5. Right? We can't round that to 2 or round it down to 1. It's 1.5. So in order to get a whole number ratio, we have to make this a whole number. Right? So this is essentially 3 halves. So in order to get a whole number, we're going to take 3 halves times 2 to get a whole number, which would be 3. But it's a whole number ratio between both of these, so we also have to multiply this other ratio by 2 to give us 2. Therefore, our empirical formula between chromium and silicon in this case is going to be Cr3Si2. Again, if we don't end up with a number that's approximately equal to a whole number, then we have to multiply by some value, both of them, to get everything to be a whole number. Let's try one more, and this is a different way we're going to determine empirical formula through a process called a combustion analysis. So terephthalic acid used in the production of polyester fibers and films is composed of carbon, hydrogen, and oxygen. So we're going to end up with an empirical formula for carbon, hydrogen, and oxygen. When 0.6943 grams of this acid was subjected to combustion analysis, it produces 1.471 grams of carbon dioxide and 0.226 grams of water. So we're going to do some analysis on this. So we're taking this compound and doing a combustion analysis, which means we're going to burn it in the presence of oxygen to form carbon dioxide and water. Right? So the amount of carbon dioxide that's produced is going to be related to the amount of carbon that is present in here. The amount of hydrogen that's produced is going to be related to the amount of hydrogen in this original compound. Right? The oxygen is going to be related to both the compound and this oxygen here. But remember that the total amount, the law of conservation of mass still applies. So if we started with this mass at the beginning, then at the end, the mass of the compound has to be conserved. So the total mass of the carbon, oxygen, and hydrogen that we have in the products has to equal this 0.6943 grams has to equal the mass of the carbon plus the mass of the hydrogen plus the mass of the oxygen. So if we can figure out how much of each one of those elements was present, we can figure out the third one, how much of that mass, what mass of oxygen we have in this original compound. Right? So we're now going to start then with this 1.471 grams of carbon dioxide and the 0.226 grams of water. The carbon dioxide is going to give us the carbon, the water is going to give us the hydrogen, and then we're going to use this equation to allow us to calculate the amount of oxygen. Right? So first thing we have to do is convert from mass to moles. So 1 mole of carbon dioxide, right, to figure out the molar mass of this, is going to give us 44.01 grams of carbon dioxide. And for the water, for every 1 mole of water, that has a mass of 18.016 grams. Right? But we don't want moles of each one of these. We want moles of either carbon or hydrogen. So we have to then look at how many carbons for each one of those. For every 1 mole of carbon dioxide, we have 1 mole of carbon that had to come from this compound. Right? And from the water, for every 1 mole of water, we get 2 moles of hydrogen that had to have come from this compound. Right? So if we do that, we're going to then do this calculation. We see that we had 0.0334 moles of carbon and 0.0251 moles of hydrogen. To figure out the amount of oxygen that we had, we have to convert this to mass, because the total mass, as we said, of this original compound has to be maintained. So the mass of carbon at the end plus the mass of hydrogen at the end has to equal the mass of oxygen. So the mass of oxygen has to be equal to this 0.6943 minus the mass of carbon that we have at the end minus the mass of hydrogen. Right? So we have to then convert these two from moles to masses. So we're going to take this 0.0334 moles of carbon and convert it to a mass, where we have 1 mole of carbon gives us a mass of 0.1 or 112.01 grams. which is equal to 0.401 grams of carbon. So in the product, or in this compound, we had 0.401 grams of carbon. And the other one, if we have 0.0251 moles of hydrogen, for every 1 mole of hydrogen, that weighs 1.008 grams of hydrogen, which would give us a mass of 0.0253 grams of hydrogen. Right? So we're going to take these two values, the amount of carbon in our original amount, and subtract it away from that to give us our amount of oxygen. Right? So this is going to equal 0.6943 minus 0.401 grams minus the 0.0253 grams, which gives us a mass of oxygen of 0.268 grams. We then have to do this same process because, remember, we're looking for the empirical formula. So the empirical formula is going to be related to the smallest whole number ratio of moles. So we have to take this mass and convert it to moles. 0.268 grams of oxygen, just like up here, for every 1 mole of oxygen, we have to have 16.00 grams of oxygen, which gives us moles, a molar amount of 0.0168 moles of oxygen. Right? Just like before, to get the empirical formula, we have to take the smallest whole number ratio, so we have to divide by the smallest number of moles present, which is this moles of oxygen. So we're going to divide all three of these by this number, 0.0168 moles. 0.0168 moles. Right? If we do that, we see that this value ends up being 2. This one is 1.5. And this one is 1. So we have, again, we have to multiply this, so they're all whole numbers, so we have to multiply all of these by 2. So we end up with a empirical formula that is C4H3O2. So these, when we do a combustion analysis, it's a little bit more complicated, but we end up figuring out the moles of everything that's present, divide by the smallest one, because the empirical formula is the smallest whole number ratio of moles.